In this session, we're going to see how Box-Jenkins or ARIMA models deal with seasonal patterns in your data. The general model that we're going to study in this session is the ARIMA 011 by 011S, which the first triplet of numbers there says we're going to use exponential smoothing to track the level of the process, and then the second part says there's going to be a seasonal component, and we're going to use that to track the seasonal variation in the data. So it's sort of like two exponential smoothing models working concurrently. And as before, there will be special cases of those exponential smoothing models in which the alpha value is set at 1, which gives you some models that use random walks to track either the level of the process or the seasonal pattern. Seasonal models have a descriptor called S that tells the number of periods it takes for the pattern to complete itself. For example, if you're looking at monthly data, S would be 12, quarterly data, S would be 4. If you're looking at hourly data within a day, S could be 24, or it could be 16, for example, if there's 16 working hours in the day in which you would be collecting data. Here's some actual data that shows a seasonal pattern in the sales of a group of stores. This could be stores that sell toys, for example, because of the strong demand, and the holiday season makes fourth quarter a business much higher. Could be baking products, it could be a large number of things. I chose this data set because it's somewhat extreme. It shows a huge leap in sales during the fourth quarter, and that sort of helps us think about the challenges that we have in making the forecast. Two things I want you to notice about this data set. One is there is that seasonal pattern. In particular, fourth quarter is much higher than the other three quarters. And the other thing is there is over time a trend in the data. It looks like the sales have declined over the last few years. So when we make our forecast, we have to capture both of those, the seasonal pattern as well as whatever changes there are in the annual sales of the stores. So look closely at the data and look at the last quarter there. It's third quarter, and we want to make a forecast for fourth quarter. Two things we'll know is that fourth quarter should be a lot higher than third quarter because of the seasonal pattern, and also third quarter of this year is somewhat lower than what third quarter last year was. So that probably means our projected sales for fourth quarter should be adjusted down a little bit below what it was last year. So if we start thinking about that, we could probably make up a pretty good rule for making that forecast, and that's what we're going to do next, and then we're going to build on that rule to get the general model that we're going to develop in this session. Even if you had never heard of ARIMA models and you were given these numbers and asked to make a forecast for fourth quarter of this year, you'd come up with a pretty simple rule, which actually is what one of our ARIMA models will do. That rule would say there's two pieces of important information here. One is last year in third quarter we were at about 25 million. This year we've dropped down to 23 million third quarter of this year, quarter 43. That would be one important piece of information. The other piece of information would be last year, from third to fourth quarter, sales jumped from 25 up to 33, an increase of about 8 million. So you'd probably say, if you had to make a good guess, you'd say take this year's third quarter sales of 23 and add the 8 million from a jump that we observed last year, and that would be our best guess. If we express that rule in mathematical terminology, what we will have defined is an ARIMA 010 by 010 sub 4 model. In other words, a combination of two random walk models. One is tracking the level of the process, the other is tracking the seasonal pattern. So first of all, you'd say, let's start with the current observation, which is going to be our guess of the level of the process. That would be Z43, the current period. And next, let's go back and look at the discrepancy between fourth quarter sales last year and third quarter sales. That would be Z40 minus Z39, and that discrepancy is about $8 million, and that's our best guess as to how much sales change between third and fourth quarter. And so now we have a mathematical formula, Z hat, which means forecast, sub 43, which means the forecast made in period 43, parentheses 1, which means one period into the future. In other words, we're forecasting what's going to happen in period 44, the fourth quarter. It says to do that, take the observed value Z sub 43 and add to that the difference between Z40 and Z39, which were fourth quarter minus third quarter of last year. And that gives us our best guess of what fourth quarter sales will be this year. I'm going to define that jump that we see between consecutive quarters as discrepancy, and I'm going to abbreviate that by D sub T. So from I've gone back to the beginning of the data now, and I'm going to start to build the model forward. And I don't have a discrepancy for period 1 because I don't know what happened in the period prior to that. But in period 2, I computed a discrepancy and found that the demand actually dropped by $1.5 million between periods 1 and periods 2. Period 3, the demand dropped a little bit more. And then in period 4, which is of course fourth quarter, the holiday season, that time we had a jump of almost $13 million. And then in the following period, period 5, which was first quarter of the second year, it dropped back down by 12 million. So that is my sequence of discrepancies, and I'm going to use them in computing my forecast. So if I'm making a forecast, I can't get started forecasting until I have a complete season of data and I start the first season of the following year. At that point, I can observe the level of the process. Let's suppose I'm in quarter 5, which is the first quarter of the second year. I can observe the level of the process, and I'm forecasting into quarter 6, which is going to be a second quarter. So I go back and get the discrepancy of second quarter last year to add to that. And mathematically that says the forecast made in period T for one period into the future is Z sub T plus D of T minus 3. So in this particular example here, I'm in first quarter of the second year, T equal 5, and the observed value at that time is about 31.5 million. And I add to that the discrepancy that I saw between first quarter and second quarter of last year. So I go back to second quarter of last year and pick up that minus 1.5 million, and that produces my forecast of 30,000. You see, there's not much of a seasonal pattern happening between the first and second, or the second and third quarter. The big jump occurs between third and fourth quarter, and then after fourth quarter back down to first quarter. So, but the general rule is given here. You go back and pick up D of T minus 3. Look first at the top of the page, and you'll see that we're talking about a different seasonal model now. we have replaced that first triplet of numbers there, P, D, and Q, with 0, 1, 1, which you should remember is shorthand for exponential smoothing. And we're going to use exponential smoothing to track the level of the process. So whereas before we used the current observation as the baseline, and we adjusted that using those discrepancies that we had observed last year, in this case we're going to track the level of the process using exponential smoothing. And you're already familiar with that. You just take the most recent value and multiply it times alpha, and the previous level multiply by 1 minus alpha. And we're going to do something else different in this model. When we compute our discrepancy, we're not going to compare the current quarter to the previous quarter. We're going to compare the current quarter to the previous quarter's level as computed using that exponential smoothing formula. So we're going to be subtracting the current quarter in column 1 from the column 2 of the previous quarter. In this case, those column 1 and 2 are the same in that first quarter because that's how the exponential smoothing got initialized. But the important thing to remember is what is in red there. You're going to use the discrepancy of the observed value from the previous quarter's estimated level using that exponential smoothing. And so now we're ready to compute the forecast. We simply take that level that we computed using exponential smoothing, and we add to it the discrepancy of 3 periods prior, and that discrepancy was the discrepancy of the actual from the level that was computed using exponential smoothing. So, for example, if we're in period 5, the estimated level by exponential smoothing is about 33 million. You notice that's quite different from what the actual value for period 5 is. And last year, period 2, which was the same period that we were forecasting into, last year period 2, this year it's going to be period 6, but it's the second period of the quarter. The discrepancy last year, going from period 1 to period 2, was minus 1.5 million. So we add that to the current level, and we get a forecast of 31.9 or almost 32 million, which would be our forecast for period 6. Okay, there are 2 important things that you want to get from this slide. The first is at the top. Notice that the second triplet of descriptors there for this model have changed. It's now a 0, 1, 1 associated with the seasonal part of the model. So not only are we using exponential smoothing to track the level, we're going to use exponential smoothing to track those discrepancies. The second thing you want to notice is we've introduced a new variable called S sub t, and S sub t is tracking the discrepancies. In other words, it's using exponential smoothing to track that, and S stands for smoothing, let's say. And the subscript is t minus 4. In other words, I'm going back a whole year each time I update that smooth value of those discrepancies. So let's pretend I'm in the 4th quarter of the current year. I would take the discrepancy that I just computed, and I would weight that with the smooth value that I had for the 4th quarter last year. So that's t minus 4 is an important number to recognize in that formula. We're going to go through an example. You don't need to stare too hard at the formula, just sort of get the general idea that we're using exponential smoothing and we're jumping back for a whole year each time we update. Okay, let's see how we get started doing that. First of all, the first discrepancy that I observe is in period 2, and then I have one in period 3 and 4, and then again in the first quarter of the second year. So to initialize and to get my first 4 discrepancies, I just have to set S sub t equal to whatever I observe. This is the way we typically start exponential smoothing, is just by picking the observed value as the initial value. So it's not until period 6 that we're ready to start updating. Now the smoothing parameter that I use to update my discrepancies we're going to call beta, and we are here using a beta of 0.4. Ordinarily beta will be found using solver. In this case I just arbitrarily chose 0.4, and I'm going to weight 0.4 times the current discrepancy that I've computed, and that discrepancy, you know, was computed by taking the actual from the level that we have. And then I'm going to take 1 minus 0.4, or 0.6, and multiply that times the smooth value S sub t of the previous year, and that number is about a negative 1.5 million. And then I get a smooth value for the discrepancy in the current period of about minus $2 million. So basically this is period 6, and we're saying how much does period 6 differ from period 5. Period 6 is the second quarter, period 5 is the first quarter. It says there's usually a drop between first and second quarter. And let's just make sure we understand how those discrepancies get updated in general. In period 6, that's the second quarter, so we're going to take the exponentially smooth average of period 6 and period 2, which was also the second quarter. Period 7, that's a third quarter, so we're going to be weighting the D sub t of this period with period 3, which was the third quarter of last year. Period 8 is a fourth quarter, so we're going to weight that with period 4, which was fourth quarter of last year. Notice those numbers look really big. Period 9 is a first quarter, and we weight that with the most recent first quarter, which was period 5. And notice in first quarter our sales drop off a lot from the previous quarter, and that's reflected in that negative 9 million there that we see as the smooth value. Let's back up and see how we make the forecast. We're going to be using the smooth level of the process, and we're also going to use the smooth discrepancies. And like before, we're going to have to go back to the previous year to get the discrepancy that we need. So in first quarter, or fifth quarter rather, we're in the first quarter of a year. So we take the level that we observe, or the level that we've computed rather, and we're going to add to that the discrepancy associated with second quarter of last year, because we're forecasting into second quarter. And that tells us that on average, or the smooth value of the discrepancy going from first to second quarter is about $1.5 million. So we combine those two numbers and get our forecast. So it's similar to what we started out doing, but rather than using raw numbers and raw differences or discrepancies, we're using smooth values for both of those. Okay, here are some formulas that look complicated, but they're really very intuitive. let's pretend I'm in the first quarter of a year and I'm making a forecast one period into the future. You already know how to do that. You just take the current level, smooth, and you take the smooth value that we have associated with going from period 1 to period 2 of last year. So that's ST minus 3. You'd say, well, what if you wanted to forecast 2 periods in the future? Well, it'd say just tack on another seasonal adjustment, and that would be the adjustment of going from period 2 into period 3. In other words, the first forecast we made at the top there was the forecast 1 period into the future. If we're going 2 periods into the future, we just go back another year and get the appropriate adjustment. So we're in period 1, we're going to be forecasting into period 3, so you take both of the adjustments from 1 to 2 and then from 2 to 3 to add to that. What if you're forecasting 3 periods in the future? Just go back and add all 3 adjustments from last year that take you from period 1 to 2 and then 2 to 3 and then 3 to 4. What if you're forecasting a whole year into the future? Take a whole year's worth of adjustments. So if I'm in period 1 and I'm forecasting into period 1 of next year, I take the smooth level and then I add the adjustment for going from period 1 to 2 and then 2 to 3 and 3 to 4 and then 4 back to 1 again. And you can continue doing this as many periods into the future as you would like to forecast. This slide is very busy, and I don't expect you to go through every single number in there. I've highlighted some numbers that I want you to look at. So if I'm in period 43, I'm at the end of third quarter and I'm making a forecast for the holiday season, which is fourth quarter. This is the problem we originally posed. And so to make that forecast, I would add the level and the S sub t, or the smooth level from associated with fourth quarter of last year, and I would get that forecast there of 32,993,000. Then if I wanted to forecast another period into the future, that bolded value 32,000, I would just bring it down and add another period which says, in going from fourth quarter back into first quarter of the following year, I need to subtract another 7,000 because that's the smooth value of that discrepancy. And then to extend it out to 3 periods into the future, I would make the next adjustment, or minus 2 million, which is the smooth value of going from first into second quarter. And then the next, to extend it to the next level, all the way around to third quarter next year, I would add one more seasonal adjustment to that. We're going to work on this in a little more detail later, so don't spend too much time trying to figure it out. The intuitive part of it is you can take the current level and just keep adding those adjustments to take you out farther and farther into the future. The model has 2 parameters, alpha and beta, and like before, we want to minimize the sum of the squared errors, and we will compute those, the squared errors in a column, and add them up, and that will be our objective. That solver would use the 2 values, alpha and beta, is what will be the decision variables in solver. The model at the bottom shows the general model that we're using. It says we're using, in all of these models, we're making the forecast using a level plus a seasonal adjustment. And at the model at the bottom, it says we're going to use exponential smoothing to estimate the level, and also the seasonal adjustment is based on exponential smoothing of all of the seasons. And then we get the special cases of that model, which are the first three there, which means you either fix alpha at 1 or beta at 1, or you fix both of them at 1. And now you have 4 different models to choose from, and you're going to use the principle of parsimony to figure out which one is the best model.